Hello and welcome to this tutorial. Today we'll be discussing how to perform a multi-step analysis in FEBio. Really, it's just the tutorial from the website, from the Knowledge Suite here on febio.org. But I figured that a video would be easier to follow than this text. First off, though, why would we want to perform a multi-step analysis? Basically, it comes down to kind of two things. First, making it as realistic as possible. For example, in my research, we use these cervical spine models, and if the nucleus pulposus inside each of the discs isn't at the right pressure, then the biomechanics don't solve correctly. And so we use one step to ramp up the pressure. And then in the next step, that is when we do all of our loading and all of our real analysis. The second reason is, for example, if you have two contact surfaces and they're complex, you may want to slowly bring them together before you do any crazy motions so that they don't accidentally go through each other because the computer doesn't patch them. These multi-step analyses can kind of be a workaround to solve issues like that. With that, let's get started. I'll open up a new window of FEBio Studio. Here it is. We're going to do a new model, and it will be a structural mechanics type problem. We're going to build our geometry. We'll do this box and position 0, 0, 0. That's perfect. And we're going to give this a width of 10 units, a height of 1, and a depth of 0.2 units. So in the x direction, 10 long, 1.2. These can be whatever units you need. In my research, typically we use millimeters, but you just have to make sure that whatever you decide on, that the scales match between your different parameters. So I'm going to say 10 millimeters here for the width, and we'll see that that affects how we define our material later on. So I clicked create, and now here it is. Looks pretty good. Let's make a mesh. We're going to come in here. The object is selected, and we're going to say, since it's longest in the x direction, we're going to give it the most elements in that direction. So nx will be 20, and y will say 5, and then z will say 3. Now, if I go ahead and apply this, there's our stats. That's how many we have. And we can see that it created this beautiful mesh. Everything looks great. They're also all exactly the same size and shape, which is great if we had everything else uniform along the material, but actually we don't. We're going to fix this left side, and we're going to apply a force on the right side. And just from experience, we know that the stresses are higher closest to the fixed end. And so to get better detail and a more accurate picture of what's happening, what we're going to do is apply an X bias. So we're going to say X bias of 1.2 and apply. There's our stats. And so now we have the same number of elements as before, but we can see that their shape has changed. So this 1.2 means that if we take the length in x of this element to get the length in x of the next one over, we have to multiply this length by 1.2. And so that compounds and gets bigger and bigger and bigger, which is exactly what we need for this case. We also could do an X mirrored bias, and so that would make it so that it was finer at both ends. We could do 0.8, and that would do the same thing but backwards. So we can hit apply, and now it just flipped it to the other side because it's the same thing. This length by 0.8 by 0.8 by 0.8, right? So we're going to leave it though at 0.2. And these are hex 8 elements, which means they're hexahedrons or cuboids. and they have 8 nodes each. So in this case, 8 nodes, hexahedron. That means there's one at each corner of the cuboid. So anyways, this is all we needed to do with our mesh was these 4 things and hit apply. So there we go. It's all ready to go. Now that that's done, let's come into our model viewer, to our steps. This is where we're going to make our 2 steps. Our first step will have a load, and then our second step will let the load go. And so it will bounce. We haven't made those yet, but there's actually already a step within steps. It's called this initial step. And this is kind of our base 0, which what this initial step does is it gathers all the things that will be applied during the entire analysis. So every, material definition, boundary condition, etc., that is on during the whole analysis starts in initial. But then everything else, we have to add an analysis step. So you can right click and hit analysis step. You can also come into physics, add analysis step right there. We want to insert it after initial. There isn't really any other option anyway. And so in this first step, we are going to apply a load, and we're going to pretend that it's static. Static means it doesn't move, right? And so it's going to be this quasi-static analysis, meaning it just uses the static kind of equations to solve everything. So we're going to leave this analysis as static. We're going to give this 5 time steps of length 0.2. So what does this time stepping do? In the similar way that we had finer spatial resolution with our more refined mesh on this left edge, the time stepping alters our temporal or time-related resolution. So if we rewind to classical finite element analysis, everything is put in all at once, and then in one step, it says, okay, you had this, you applied all these loads, and boom, you get this, and it solves it all at once. That's really hard to do with large deformations or hyperelastic materials like we frequently deal with in the body and biomechanics in general. And so to counteract the issues that come with trying to go all at once, such as, maybe it accidentally calculates that things are like bumping inside of each other or themselves, things like that. To get around that, we gradually add our loads at different time steps. And so in this step, we're going to have 5 time steps, so broken down into 5 chunks, and they're going to be 0.2 seconds long. So 5 times 0.2 gives us 1 second in our simulation time. Another thing we're going to do, we're going to scroll down here and we're going to turn off the auto time stepper. What does the auto time stepper do? So when we apply our loads, and let's say it goes 1 step in and it kind of runs into an issue, then there are a number of things it can do to say, okay, maybe that step was too large. Let's work it back a little bit. And so we'll add steps or decrease the time scale, things like that as needed so that it can make it safely to that final point. For this step, we are confident that our 5 steps will be totally enough. So we're just going to turn this off. However, we're going to leave that on for our other time step. Let's get that started. So again, right click, add analysis step, and we're adding this one after step 1. This will be step 2. And this is the one that we're going to make dynamic. We're going to make it 40 time steps long at 1 second intervals. So this means, okay, 40 times 1, 40 seconds, plus our previous time step, so which was 1 second. So we have 41 second simulation in all. And all this, we're going to leave this on. This is fine in the models that I work with. We really get into, probably 10 or 15 retries, changing the maximum and minimum step size, turning on aggressiveness and things like that. to really help it get through the difficult parts of its solving. But right now, we can just leave that as is. Okay, so that's our time steps. Let's come in and add our boundary conditions. So we can come to boundary conditions, right click, or we can also come to physics and add nodal boundary condition. So this is how we're fixing the left side, is we're adding a nodal zero displacement boundary condition. So we'll hit OK, and we're gonna fix it in the X and the Y and the Z directions. If you don't include all three, then it might try to like shift a little bit in a certain direction, but without any real guidance on how much or how little it's allowed to shift in that direction, it will get really angry and it will either take a super long time or give you bizarre results or just crash. And so we want to make sure that it knows exactly how to move in all directions. So we're going to fix in all directions here on this side. So there it is. And we want this to be part of the initial time step because we want this on the whole time. And we're going to scroll down. It's all set up except for we have to tell it which face to apply it to. So we're going to do our select faces, select this one, and add surface 4 to our zero displacement 1 boundary condition. Excellent. I'm clicking off of that so that now we can come to the other side and we're going to add another one. This time though, it's not going to be a nodal boundary condition. Oh, yeah. It's going to be a surface load, which there it is. Hard to find sometimes. Surface load, and we're going to make this a traction. We could have done nodal, we could have done a pressure, things like that, but the beauty of a surface load traction is that it will be the same no matter the area or the number of nodes of the surface. It will just give this many newtons of force applied across the entire surface. And so this one, we want to be not part of the initial time step because we don't want it on the whole time. We want it to be just with step 1, so that first second. Here's our scale. What this does is it is a multiplication factor for the traction vector right here. So in here we have 0 for X, 0 for Y, 0 for Z. We're going to move it or push it 1 Newton in the negative Z direction. So we're going to say -1 in that. And then our scale is a multiplication factor. And this little symbol next to it shows that there's a load controller associated with it. So to look at that, we're not going to change it, but just to look at it, we can come up here to our curve editor. And just like in our model viewer, we have loads. So loads, we're going to drop down the menu, traction 1, okay, traction 1. And then inside traction 1, there's scale. So just like how inside traction 1, there's scale inside traction 1. And here's the load controller, LC1. We hover over here. Oh. If we hover over here, we can see that it will tell us the name. LC1 is our load controller. I'll come right back. And so as I said before, this is how it ramps up the load over that 1 second. So on our x-axis, we have time. On our y-axis, we have the scale. So from 0 to 1 second, it ramps up linearly. And we can change this. We could say, okay, make it a step, smooth, etc. And we could say, actually, I don't want it to be -1. I want you to multiply it and make it 1.4 in the end or whatever. We want to leave it at 1 for this. I also want to make the point that we could totally use the load controller and not use extra steps. So if I were to add, I'm holding shift and clicking, that adds a point, and we could drop this down. You can use this magnet so that it snaps. We could have it ramp up and then turn off. using the load controller. And that would do the same thing as having this load only be part of step one and adding another step for later. But using the steps like in the tutorial allows it to be easier, like followed. Someone can come in and say, okay, this step happens, instead of going, something turned off. Oh, it was in the load controller. But that's just multiple options. So I'm going to select this and delete. And so back to normal. There we go. So didn't really change anything. Can exit out. And so we have the surface selected. Excellent. And that's it. It's part of step one. So we're set. Our boundary conditions are ready to go. And so now all that's left is adding material. You can do that either by right-clicking here or come to physics, add material. And I'm just going to search for Neo-Hookean. So this is essentially the most simple material type in FEBio. So we're going to say 25,000 for Young's modulus, Poisson's ratio of 0.35. The Poisson's ratio doesn't have units. This is just the ratio of how much it like shrinks in as you stretch it. And the Young's modulus, though, this one does have units. So in our millimeters, newtons, seconds scale that I like to use, value of 25,000 newtons per millimeter squared, that turns into 25 gigapascals. So 25 gigapascals, 0.35 Poisson's ratio. This is some sort of like a copper nickel alloy or something, some sort of metal like that is what this would kind of represent. So that's our parameter values, but we haven't added it to anything. So I'm gonna select the part. There we can see the white bracket, so it's selected now, and just hit plus. It turned orange, so we know it applied. And we're ready to go. So I'll hit Control S to save the FS2 file, which is the FEBio Studio 2 file. So that saves all of the settings, everything in FEBio Studio. And so I'll just save that to my desktop, and I'll just leave it as Model 1. You can rename it whatever you want. Okay, that's good to go. And now we're going to run it. So we can click here, run FEBio, or come to FEBio, run. So I'll click here. And now it's asking, what am I going to name the files that it uses to run and actually process what we set up in here? So this is going to make a FEBio file, or .feb, which is different from the FS2 file that we just made. The .feb file is an XML file, sort of like a text file, and it has just everything listed in a giant like sheet. And you can go in and you can edit parameters in there, but that's what actually goes to the solver. It also will create a log file where it shows all the stats and all the information from as it was running, as it was solving. And then it will also create a .xplt file, or xplot, which is the output file that we'll be reading in here in a second. And so you can rename all those, they'll all have the same name. You can rename that here. And you can see that it's going to save it to my desktop and then jobs. So it's making a folder, a jobs folder inside my desktop to put all that. All right, so no need to change any of that. You can just hit run. We can see in the upper left-hand corner, it's progress. Okay, so we have our job monitor. We have a normal termination. It made it all the way to 100%. So we're set. I'd like to talk about these warnings. There are some warnings. It said the max number of iterations was reached, so the stiffness matrix was reformed. Basically, it did have a little bit of trouble as it was moving through those time steps, but it was totally fine and it fixed it. So warnings, but no errors. We're chilling. So we'll open results, and here it is. I'm going to close notes and output so that we can look at the timeline. So I'm going to use my arrow keys to click through, We can see the force is ramping up, just like we set up in our load controller, up until time equals 1. And then from here, it's going to release, and we'll see the dynamic response. And so there it is, and you can see it kind of wobble and flop. That's because the dynamic analysis includes things like inertia and density and mass and things like that. And so there it is. We can also come up here and look at stress. For example, effective stress. You can see, yes, the highest stresses are at the base. And so it's a good thing we increased our spatial resolution with our finer mesh right there. You can also look at, for example, displacement, say, okay, how high up does it go? How low, etc. And so we can see this is the max height, this is the minimum height. And we can change some of this by selecting color map over here. And yeah, I recommend you play around with some of these parameters to see how it changes. But that wraps up our tutorial. Thank you so much.